Alrighty then. So as promised, I'll go through this note-taking guide and try to shed some light on intermolecular forces and phase changes and how intermolecular forces and phase changes are related, and then subsequently heating and cooling curves, which are a pictorial representation of the energy that are involved in the processes of phase changes, although phase changes are not the only thing that intermolecular forces are related with. So I guess I don't want to keep going up and grabbing the red font, so I'll just cruise along. So this video right there, Bozeman Science, the guy clips along fairly quickly, and I don't think I will play the video right here on this so you can see it in the screencast. I'll just leave that to you. I will just fill this stuff out. So during the video, and as we have mentioned before, some examples of physical properties that are impacted by IMFs are boiling point, melting point, surface tension. Oops, I already had tension over there. This one's one that I don't typically list, although it certainly meets the criteria. That would be capillary action. Vapor pressures inevitably on my list. And I believe this one is volatility. Wait a minute, let's put viscosity. Vapor pressure and volatility are similar. So I'm going to put it in there, volatility. Okay, so this little deal right here is nothing more than to keep students focused while they're watching the video and not dream around. So it's intermolecular forces explain the difference in an ideal gas, oops, missed, and a real gas. Don't worry much about what an ideal gas is, what a real gas is. We will study ideal gases. Well, there'll be a whole unit on gases, and we'll get all up in it. So, as we've mentioned before, intermolecular forces are the forces between molecules, whereas intramolecular forces are the forces within the molecule itself. Increasing strength of IMFs cause molecules to move. If you increase the force of attraction between the molecules, it will make them move closer together. Oops. And the flip side of the coin is if one decreases the strength of IMFs, it causes the molecules to move farther apart. So in changing from a liquid to a gas, the stronger the IMF makes it harder. And this is a key point right here. In going from a liquid to a gas, the process requires that IMFs be broken. And the stronger the force of attraction, the more energy required to break that bond, if you will. Thus, the harder it is to move from a gas to a liquid. Excuse me. Molecules with strong IMFs have a high surface tension. Let's see, vapor pressures. Vapor pressure measures the amount of gas in a closed system, how easily it will evaporate. Vapor pressures come from volatile liquids. high volatility results in IMFs with weak strength. And we'll discuss that a little more. That is spelled incorrectly. So these relationships are reasonably important. As IMF strength increases, boiling point increases because the more energy is required to break the IMFs. Similarly with melting point. Similarly with surface tension. Surface tension can be thought of as how tightly the molecules, or how much the molecules are attracted to one another at the surface. So substances with high surface tensions can have things happen like water bugs scoot around on top of them without sinking because they have a high surface tension. If you take a water bug, we called them water skeeters where I grew up. If you take a water skeeter that can literally walk on water and put it in an alcohol, it will sink because the surface tension of the alcohol is not high enough to hold the bug up. Let's see, as IMF strength increases, viscosity increases. Viscosity is how thick the liquid is, how much it resists flow. And this one, vapor pressure, is the pressure of a vapor, but the impact on vapor pressure is that as a substance vaporizes and becomes a gas, that gas subsequently exerts a pressure. And so the more of that gas that is in a confined space, the higher the pressure. And we'll get all up in how gases exert pressures and all that stuff. But substances that are easy to turn into the gas phase have a high vapor pressure. Alternatively, substances that are difficult to get into the vapor phase have a low vapor pressure. So as IMF strength increases, vapor pressure decreases. Alrighty then. And then we need these terms, the following terms. And the reason being is that phase changes are energetic processes. They involve the absorption of energy or the release of energy. And these are the terms that go along with that. So exo from biology means outside. An exoskeleton is a bug that the skeleton's on the outside of its body. So outside heat. So an exothermic process is one being the process that releases energy. I guess you could say, I'm just going to say releases energy. That's all I'm going to say. If you're holding an exotherm in your hands, it will feel hot. Alternatively, an endotherm or an endothermic process is one that absorbs energy. If you have an endotherm in your hand, it will feel cold. And the reason it feels cold is the process is absorbing energy in the form of heat, and your hands are the source of that energy, so it makes you feel cold. So melting is the phase change associated in going from a solid to a liquid. In the process of melting, intermolecular forces are broken, as necessarily melting then becomes an endothermic process, because energy IMFs are broken. Energy is required to break bonds. Therefore, melting is an endothermic process. Freezing, on the other hand, is when a liquid turns into a solid, in which case intermolecular forces are being formed. And the formation of a bond or a force of attraction releases energy. As such, freezing is an exotherm. In an odd sort of way, freezing is a warming process because freezing gives off heat. Let's see, vaporization, that is the phase change going from a liquid to a gas. That process involves the breaking of intermolecular forces. As such, it is an endotherm. And by the way, I call endothermic processes and exothermic processes endo and exotherms all the time. Let's see, condensation is the phase change going from a gas to a liquid, in which case intermolecular forces are being formed, or forces of attraction are being formed, which releases energy, so that is an exotherm. Sublimation is going from a gas to a solid, which is breaking intermolecular forces, so that would be an endotherm. And I don't have their bad teacher, no biscuit. Deposition. Deposition is the process of going from a gas to a solid, and in which case IMFs are being formed, so that's an exotherm. Okay, why are melting, vaporization, and sublimation endotherms? I already mentioned that in my delightfully articulate description of these phase changes. Let's see. These processes are endotherms. I just looked up there and saw exotherms and went, oh no. No, it's right there. Endotherms. Endotherms because they all involve the breaking of IMFs, which require the absorption of energy. Okay. Alternatively, freezing, condensation, and deposition are exotherms because they all involve the formation of IMFs, ETHERMS, the formation of IMFs, which releases energy. Bong, oops, energy. What is volatility? Volatility is the tendency, oops, of a substance to turn into a gas. Highly volatile substances evaporate quickly. So how are volatility and IMF strength related? This would get back to when you're posed a question like this, address the answer in the same way all the time. There are two variables, volatility, IMF strength. So one says at volatility and IMF strength are, and the responses, and this is frustrating because I can't make you tell me what they are. They're inevitably one of two things. They're either directly related or inversely related. So let's see. Volatility is the tendency to turn into a gas. So turning into a gas involves the breaking of IMFs. So substances with strong IMFs are more difficult to turn into a gas. So volatility and IMF strength are inversely related. Bong. If you were to say something about that on a test, and this happens all the time, even after I've said what I'm about to say many times, what students will say is that as volatility increases, as IMF strength increases, volatility decreases. And I will reply, and question mark X. What about when IMF strength decreases? Which would be the follow-on question. And so to avoid having to say all that, if one says inversely related, then you've said everything that needs to be said. Okay, vapor pressure. Vapor pressure is the pressure of a vapor. The pressure, oh man. Nice. The pressure exerted by the gas phase of a substance. So water evaporates, turns into a vapor. The pressure exerted by that gaseous water is the vapor pressure of water. So, how are vapor pressure and IMF strength related? IMF strength and vapor pressure are also inversely related. On account of because vapor pressure is the pressure of a substance that has the gaseous phase of a substance that has turned into a gas. And to turn a substance into a gas requires the breaking of IMFs, and strong IMFs are hard to break. Yeah, that would be the ticket. Boiling point. The boiling point of a substance is the temperature at which a substance boils, which is like, oh, seriously, Pace, that's the best you can do? No, it's not the best I can do. Technically speaking, the boiling point of a substance is the temperature at which the vapor pressure of a substance equals the atmospheric pressure. So the pressure, you're going to boil a beaker of water or a bucket of water, or a pan of water, whatever. So you put this beaker of water on the hot plate and flame on with the Bunsen burner or the hot plate, and energy starts to go into the water, and the kinetic energy of the particles increases, and yippee skippy. what's preventing the substance, at least in part, from evaporating virtually immediately is the atmosphere pushing down on the surface of that water that's in the beaker. So when the vapor pressure of the substance is equal to the pressure that's pushing down on the liquid, then at that point, the substance, in this case water, will turn into a gas right down in the body of the liquid. There will be a gas bubble form right down in the water, and up it will go, and voila, boiling occurs. So that's what that business right there is the temperature at which the vapor pressure of a substance is equal to the atmospheric pressure. And the normal boiling point is the temperature at which a substance will boil at sea level, or 1 atmosphere of pressure. And we will talk about atmospheres of pressure a lot when we get into gas laws. But the normal boiling point is kind of a comparison for other boiling points of substances, and so the normal boiling point is the temperature it boils at sea level. If one were to check the boiling point, for example, of water at sea level and at the top of Mount Everest, they would boil at significantly different temperatures because the atmospheric pressure at the top of Mount Everest is much lower than the atmospheric pressure at sea level. And there you go. Explain why substances with different IMFs have different boiling points, or melting points, or viscosities. Use the term kinetic energy in the response. This is an important deal I've got going on here. So, when these things start to happen, things start to boil or melt or freeze, or those phase changes happen. What's really happening at the molecular level is, for example, a substance is being heated up and it's about to boil. What's happening at the molecular level is, as heat is going into the substance, the kinetic energy of the particles of the substance increases. And the kinetic energy of the substance continues to increase as the temperature goes up. And so they jostle around, the molecules jostle around and slam into one another and begin to slam into one another more violently. Well, as this is happening, this increased kinetic energy and the jostling of the molecules starts to have an impact on the intermolecular forces. And when there is enough kinetic energy in the molecules or the particles of the substance to overcome the IMFs holding the substance together as a liquid, the substance will boil, or it will turn into a gas. So again, when the kinetic energy of the substance or the particles of a substance gets high enough to overcome the intramolecular forces that are holding the substance as a liquid, particles will escape into the vapor phase. Likewise, when melting, the particles of the solid begin to gain more and more kinetic energy, and they start to vibrate more and more and more and bump into one another more and more. And when they gain enough kinetic energy to overcome the forces, the intermolecular forces holding them as a solid, then they begin to turn into a liquid. So, when the kinetic energy of the particles of a substance increase to the point where the Ke overcomes the IMFs of the phase, solid or liquid, the particles, the substance will change phase. Boink. What causes a substance to sublime? Kinetic energy. That would be when the kinetic energy of a particle or a molecule at the surface of a solid gets enough kinetic energy to overcome the forces of attraction of its neighbors, it will leave the solid and turn into a gas. The IMFs with its neighbors. The particle will leave the surface of the solid and become a gas. Bunk. So all of this stuff is energy, 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 and the exchange of energy, and how energy and matter are related, which this education is neck deep in fancy terms like essential questions. There isn't more of a essential question of meaning to chemistry than how are energy and matter related. That would be a whopper of an essential question. Let's see. Substance that's sublime, water. Ice. Ice will sublime. And you've all seen it happen, whether you are aware that you've not seen it, but you have witnessed a patch of ice outside that reduced in size and the ambient temperature never got above freezing. And so if the ambient temperature never got above freezing, there's no way in God's green earth that patch of ice could have melted, yet that patch of ice got smaller. And the way that patch of ice got smaller is it sublimed away. Dry ice, this is kind of a famous one. Dry ice will sublime, and dry ice is solid carbon dioxide. Iodine, solid iodine will sublime, but those are, there you go, there's a couple of them. This is an example of a heating, or cooling curve. And I guarantee you, you will see these. You'll see these on the upcoming test. You'll see them on the midterm. You will see them. And what you will be, the questions that will be posed are there's quite a few of them. So what you really need is to understand what this picture is saying. And so you can just figure out what the answer to the question based on whatever it is. Because I can come up with a million different questions on a heating and cooling curve. So what this heating curve is saying is, okay, here's this ice. This is a heating and cooling curve of water, and the ice is at some temperature below freezing. So it's ice. And on this axis, so this axis is temperature, and this axis is heat being added. So you, at this point in time right here, you put the ice on a source of heat, and that heat you just turn it on and leave it on. and let her rip and start monitoring the temperature of the substance, in this case, ice. Well, ice will begin to heat up, and it will begin to heat up, and it will heat up, and it will heat up. And in this heating up process, the kinetic energy of the molecules of water, in this case the ice, the kinetic energy of those molecules will increase. And temperature, as you recall, is in fact the measure of the average kinetic energy of the particles of a substance. So there you go. Temperature, kinetic energy on this axis they're one and the same. So temperature and kinetic energy are increasing. And at that point, there is a flat spot in the curve where temperature remains a constant, although heat is still being added. And I would submit that conventional wisdom would say, well, you start adding heat into it, and the heat will just keep going up and going up and going up. But yet, the temperature plateaus once and plateaus again. And the question would be, why? Why, pray tell, is the temperature a constant from right there to right there as heat is being added? So this axis is sometimes labeled as time, given that there is a heat source. So the temperature remains a constant right there. And the question becomes, why? And subsequently, blah, blah, blah. I will explain. I won't just blah, blah, blah. You go farther along the curve, and after the substance has melted and turns into water, the water then begins to heat up and will continue to heat up, and the kinetic energy of the particles increases till it gets right there, and then it will begin to evaporate or boil, depending, it's boiling if you've got it hot enough. And the temperature will remain constant until right there, and right there is when all of the substance has evaporated, and then it will turn into steam, and the temperature of the steam will increase. So, I've got to use the term kinetic energy, piece of cake. Kinetic energy increases with increasing temperature. So in the curve, kinetic energy increases with increasing temperature. What would be handy would be this curve labeled as point A, B, C, D, E, F. And then we could say, well, in segments A, B, and C, D, and D, E, and segments A, B, D, E, and F, G, in those segments, kinetic energy is increasing. In this flat part right here, that's where I'm going to get potential energy in the game. So, at the end of the day, a chemical bond, however you stack it up, be it a covalent bond, an ionic bond, a metallic bond, a force of attraction, a intermolecular force, is potential energy. And I will illustrate that with the idea of, why do you eat anything, a Snickers bar, other than it's yummy and you're hungry, but there must be some driving need to consume food. And that, when I ask what is that driving need, someone in the room will tell you or tell me that you need energy. And it's like, yes. And where is the energy in the Snickers bar? And the discussion goes, and ultimately it boils down to the energy in the Snickers bar, or the T-bone steak, or the cashews, or the yogurt is in the chemical bonds of the substance. It is stored in the chemical bonds, and potential energy is stored energy. So, in this phase change right here, and by the way, the freezing, melting, in the phase change, the potential energy during the phase, I'm going to write that down, during the phase change, the phase changes, both of them, the heat, the energy is being used to change the potential energy of the system. Changing the potential energy, what's wrong with that? It was underlined red. Changing the potential energy of the system is, in this case, breaking IMFs. Boink. I probably don't even need that because that's IMFs plural, not possessive. I think. Where's Keto when you need her? And that is, there you go. That's it. I've got kinetic energy, potential energy, and phase change in that. What I would strongly suggest is you conceptualize what's happening at the molecular level along that curve right there. The heat of fusion. Heat of fusion is the amount of energy required to melt a given amount of a substance. Crap. I don't really like the way I word it. It is, how about if we just delete all that and say the energy required. The energy required to melt a given amount of a substance. And vaporization is much easier to deal with conceptually because the term vaporization has meaning. It means, to all y'all, it means turn from a liquid into a gas. Fusion is like, wait. What does that mean? And the best I've got is the reverse. When you're on this heating and cooling curve, if you're doing the cooling part, if you're going this way and the gas is cooling down and then begins to condense and potential energy is changing because IMFs are forming and energy is released, and subsequently after condensation, the water cools off and you're doing this freezing thing. When a substance freezes, the particles get essentially fused together or locked in place, but the fused together is the part I was after to go with the heat of fusion right there. That's why in Pace's mind, this melting is the heat of fusion, is because melting is the opposite of freezing and vaporization is the opposite of condensation. So fusion, melting and freezing and heat of fusion are tangled up with one another, and vaporization and condensation and heat of vaporization are tangled up with one another. The energy required to vaporize a given amount of a substance. So this says, why is delta H of vaporization typically larger than delta H of fusion? And delta H is nothing more than, I'm going to copy and paste. Delta H is the change in enthalpy You're welcome, is the change in enthalpy. We'll just call it heat for the time being. So it's the change in heat. So, but it is an energy, but it's technically, we'll get into it in heat of reaction, but it's the change in energy involved in that process right there and right there. So delta H of fusion is the amount of energy involved in the freezing or melting, and delta H of vaporization of the amount of energy involved right there. And so what this says right here is, why is delta H of vaporization typically larger than delta H of fusion, is saying, why does it require more energy to melt stuff than it does to boil it? That's what that says right there. And the reason is, and if we were there together, I would make you tell me. The reason is, oh, God, Lord, I'm out of breath. The reason is that in the melting process, some IMFs have to be broken, whereas in the evaporation process, all of them have to be broken. So there are more forces of attraction broken in the melting process than in the evaporation process. So delta H of vaporization requires more energy than delta H of fusion, because vaporization requires all IMFs to be broken, whereas in melting, only some IMFs must be broken. Bunk. Alrighty. What's the freezing point in the heating and cooling curve above? Right there. What's the freezing point? Well, the freezing point is right there or right there. It's all the same temperature. Or the melting point is right there or right there, and that would be at 32 degrees. So right there, you write 32 degrees, F. And what is the boiling point? That would be right there or right there, because the boiling point and the condensation point in terms of temperature are the same thing, and they would be at 212 degrees F. And you write those right there. And then must be broken. And right here you say arrange the following in order of increasing boiling point. Sulfur dioxide, methane, and water. This will happen on the test, I guarantee it. There will be questions that say, do that. Arrange them in terms of increasing boiling point, or increasing melting point, or increasing or decreasing vapor pressure, or whatever. Some of that will happen. And the deal is, it's all tangled up in IMFs. So increasing boiling point, if we're going to boil something, we're going to have to break IMFs. And so the stronger the IMF, the harder it will be to break. So what we're going to do is we're going to arrange those things in order of increasing IMF strength, which is why I had you do that on that practice yesterday. So sulfur dioxide, SO2, that is sulfur in the middle, 2 oxygens on the outside of it with a lone pair on the sulfur, and double bond to one of the oxygens and a single bond to the other. And so that is a bent molecule, and it has dipole-dipole interactions in the sulfur dioxide. Methane, on the other hand, is CH4. That's tetrahedral. It's symmetrical. And not only is it symmetrical, the carbon-hydrogen bonds themselves are non-polar. So there are London dispersion forces only. There are London dispersion forces in sulfur dioxide, but the dominant IMF in sulfur dioxide is dipole-dipole. Water, on the other hand, is hydrogen bonding. So to arrange those guys in order of increasing boiling point, I will put the one with the lowest boiling point first. And I will say that has a lower boiling point than sulfur dioxide, which has a lower boiling point than water. And we will be done. Whew, that was hardly any trouble at all. So there you go. This is how IMFs and physical properties are related, at least in terms of the energetic physical processes or physical properties. And take care then. Bye-bye now.